Good morning. Today we are going to discuss frequency shift keying. Frequency shift keying, right? Frequency shift keying, modulation and demodulation. So, first of all, what is the definition of frequency shift keying? The definition of frequency shift keying is the frequency of the carrier signal is varied according to amplitude of input data signal. The frequency of the carrier signal is varied according to amplitude of input data signal. That is the definition of frequency shift keying. So, what is the use of this frequency shift keying generally? All the digital modulation techniques are used to digital to analog converter. Please remember, all the whatever it may be, PSK, ASK, FSK, QPSK, all the modulation signal schemes is used to convert digital to analog. Right. Now, today we are going to discuss FSK, frequency shift keying, modulation and demodulation. We know the definition here. The definition is, once again I am repeating, the frequency of the carrier signal is varied instantaneously, okay, according to amplitude of input data signal. That is the definition of FSK. Now, this FSK I am call it as BFSK. BFSK. So, what is the meaning of B? Binary phase shift keying. So, here binary phase shift keying means in M-array scheme, right, the M is equal to 2 power n, where small n is equal to 1, here I am getting M is equal to 2 levels, that is bit number 1, bit 1 or bit 0, only 2 levels. At a time for single TB duration or single symbol duration, we can transmit only 1 bit. So, that is why here I am going to discuss BFSK, binary frequency shift keying. Okay. Now, the block diagram of BFSK is, see here, the block diagram of BFSK, it consisting of two local oscillator carriers, that is A cos 2 pi Fc1t, its frequency is Fc1. Second local oscillator carrier A cos 2 pi Fc2, its frequency is Fc2. So, here I am writing Fc1 is greater than Fc2. The frequency of the local oscillator is higher than the frequency of the local oscillator 2. Okay. Now, this two local oscillators is given to multiplexer, 2:1 multiplexer. So, two inputs and it produces single output, that is FSK output, BFSK output. And the selection line is a input binary sequence, that is input binary sequence 1 and 0 input data. It is also called as input data. This input data is given to polar NRZ. In polar NRZ, we know that symbol 1 will be mapped to plus A volts, symbol 0 will be mapped to S minus A volts. I am writing here plus A volts is equal to 1 volt and minus A volts is equal to minus 1 volt. So, the input binary data is given to polar NRZ. Polar NRZ will produce plus 1 volt or minus 1 volt depending on input data stream, right. So, this is act as a selection line. Now, see here, in this case, see here, when the symbol 1 is input binary data, that is given to polar NRZ. So, it produces plus 1 volt, okay. This plus 1 volt is given to mux. So, whenever you find bit 1, this is my bit 1, polar NRZ output, this is polar NRZ output. So, my switch is connected to local oscillator 1 and it produces output, switch is connected to local oscillator 1, it produces output of BFSK is A cos 2 pi Fc1t, right. Second one, for bit 0, the polar NRZ output is minus 1 volt. So, the selection line, the switch is connected to local oscillator 2 and it produces output is BFSK equation is minus A cos 2 pi FCT2. Okay, right? Please, once again I am repeating, if the input binary sequence, input data, that is bit 1, polar energized output is plus 1 volt. So this switch is switch, right? The switch is connected to local oscillator 1. So BFSK output is A cos 2 pi FC1T, and bit 0 is bit 0, the bipolar energized output is minus 1 volt. Local oscillator output, that is switch is connected to local oscillator 2. The BFSK equation is minus A cos 2 pi FC2T, right? Now, so now we can see the waveform of BFSK. See here, this is my input binary sequence 101101. So here I am called it as BFSK we are discussing here. BFSK means at a time for single TB duration only one bit will be transmitted. Here in this case the symbol duration T is equal to bit duration TB. So at a single TB duration we can transmit only one bit, either it may be 1 or either it may be 0, right? So this is my input binary sequence. This input binary sequence is given to polar energized. Input binary sequence is given to polar energized. So output of polar energized, see here, bit 1 is mapped to what? Bit 1 is mapped to plus 1 volt. So this is plus 1 volt. And bit 0 is mapped to minus 1 volt. So it is given to minus 1 volt. Next after TB duration, here these are the 2 bits. 2 bits are 1 1. So here again it is mapped to plus 1 volt up to 4 TB duration. Next, after 4 TB duration, bit is 0, that is mapped to minus 1 volt. Right? After 5 TB duration, the bit is 1, it is mapped to plus 1 volt. So this is polar energized. Next one, in the block diagram we are using 2 local oscillators. The first local oscillator 1, its frequency is FC1, that is A cos 2 pi FC1T. Second one is local oscillator 2, that is A cos 2 pi FC2T. So here I am taking 2 frequencies of the local oscillator. Local oscillator 1, this is my A cos 2 pi FC1T. Second one, local oscillator 2, A cos 2 pi FC2T. Right? Now see here in this case. Now I said here in this case FC1 is greater than FC2. So that the frequency of local oscillator is higher than frequency of local oscillator 2. Right? Now the output of FSK, just now I said if bit 1 is transmitted, FSK output is A cos 2 pi FC1T. If bit 0 is transmitted, FSK output is minus A cos 2 pi FC2. Now see here, this is first TB, the first TB, the bit is 1. Bit 1 means first local oscillator output will be here. Right? Next. Now bit 2. Bit 2 is the second local oscillator output. Next again bit 1. Again bit 0. Again bit 1. This is our BFSK output, right? Bit 1, this is plus 1 volt, minus 1 volt, okay? Clear? This is BFSK. Now, the detection of BFSK I am going to discuss. Before going to, after a detection of BFSK only I will discuss the, see here, the bandwidth of BFSK. Bandwidth calculation of BFSK, bandwidth calculation of BFSK, right? Here also single TB duration, 0 to TB. this is shifted towards TB by 2 minus TB by 2. Fourier transform of this one is TB by 2 minus TB by 2. Fourier transform is, we know that it will be a sinc function. Okay, frequency f. This point is 1 by TB. Here this function is minus 1 by TB, right? So here I am only taking this main lobe. Okay, now see here, this one is multiplied with a cos 2 pi fct, right? So a cos 2 pi fc1t and a cos 2 pi, second case a cos 2 pi fc2t. So because of that one, here finally this one I am writing, this is major lobe, that is 1 by TB, here minus 1 by TB. So this one is multiplied with two frequencies. So here this is FC2 and this is FC1. Similarly, negative side also, this is S minus Fc1, here this is minus Fc2, right? Now these two bits, now this one is multiplied with this one. So here for bit duration 1, for bit duration this one. So here you will get Fc1 plus 1 by TB, here Fc1 minus 1 by TB. Here also Fc2 plus 1 by TB, Fc2 minus 1 by TB. Similarly, same this one also. Now the bandwidth is highest frequency minus lowest frequency, that is Fc1 plus 1 by TB minus Fc2 plus 1 by TB, right? Now the bandwidth of BFSK is Fc1 minus Fc2 plus 2 by TB. This is the bandwidth of BFSK. Okay, bandwidth of BFSK, remember. Next, I am going to discuss here detection of BFSK. The detection of BFSK, it consisting of two methods. One is coherent BFSK, another one is non-coherent BFSK. Already we discussed what is the meaning of coherent. Coherent means synchronization between transmitter and receiver. So whatever the frequency you are using at the transmitter, the same frequency will be used at the receiver. So extra local oscillator carrier we are used at the receiver in coherent. In non-coherent, need not to use extra local oscillator signal at the receiver side. Now I am going to explain here coherent FSK, right? Now the block diagram of coherent FSK, it consisting, that is a S of t, that is modulated signal S of t, that is given to two product detectors. These two are the product detectors. First product detector is multiplied with local oscillator 1, that is A cos 2 pi fc1t. Second product detector is multiplied with another local oscillator, that is A cos 2 pi fc2t. And these two local oscillator of the product detectors is passed through low pass filter 1 and low pass filter 2. The output of two low pass filters is given to summer and output of summer is given to decision device. Here the decision device internal level is V threshold voltage is equal to 0 and it produces demodulated FSK. Okay, let us see here the operation of this demodulation. For example, we can assume here the BFSK bit 1 is transmitted, BFSK output is S of t equation is A cos 2 pi Fc1t. So this signal is multiplied with two product detectors with the local oscillator carrier. Now first, product detector 1 output is BFSK signal, that is A cos 2 pi Fc1t is multiplied with local oscillator 1, that is A cos 2 pi Fc1t. It becomes A square cos square 2 pi Fc1t, right? Now the output, see, if you see the output, so it can be written as A square by 2 1 plus cos 2 pi 2 Fct by 2, right? So here this output is A square by 2 plus A square by 2 cos 2 pi 2 Fct. By passing through low pass filter 1, it allows only low frequency signal, that is A square by 2, right? Now product detector 2 output. Product detector 2 output is A cos 2 pi Fc1t, this is BFSK modulated signal, is multiplied with local oscillator 2, that is A cos 2 pi Fc2t, okay, right? The resultant is A square cos 2 pi Fc1t into cos 2 pi Fc2t, right? Now the multiplication here, A cos B is equal to cos A plus B plus cos A minus B by 2. So I am writing here A square by 2 into cos 2 pi Fc1 plus Fc2 of t plus cos 2 pi Fc1 minus Fc2t, right? Now by passing through low pass filter 2, now the carrier itself, it is a high frequency signal. The carrier in the sense it consisting of, for example, Fc1 is equal to 10 megahertz and Fc2 is equal to 5 megahertz. The difference between is a 5 megahertz. So itself it is a very big high frequency, so that the low pass filter doesn't allow these two signals. The output of low pass filter is 0. Now the summer output is low pass filter 1 plus low pass filter 2 is equal to A square by 2. Now the decision device will compare with internal level threshold voltage 0. This value is greater than 0, so that output of the decision device will produce the output in the favor of bit 1. See here bit 1 we are transmitted, the resultant signal is bit 1 we produced, the demodulated signal also bit 1. Similarly, here I want to just mention here, if the bit 0 is transmitted, the output of the local oscillator, the S of t is minus A cos 2 pi Fc2t, right? If this signal is multiplied with the local oscillator F1 of t as well as this F2 of t, right? Because of this is multiplied with, okay, this one here you will get two different frequencies, A cos 2 pi Fc1t, A cos 2 pi Fc2t, right? So this output of the low pass filter doesn't allow these two signals. Second case, this one is multiplied with this case, right? So here you will get, for second case, minus A square by 2 1 plus cos 2 pi 2 Fct by 2. Right? By passing through low pass filter, here you will get A square by 2, and this is not allowed by the low pass filter. This A square by 2 is less than 0, so that output of the decision device will be produced bit 0. So I am not derived this second case, okay? You will try to derive this second one. I am just here once again I am telling, For bit 0, S of t equation is this one. This one is multiplied with local oscillator product detector 1. So this frequency is differ. So low pass filter doesn't allow the signal. That is, here you will get a square by 2 cos 2 pi fc1 plus fc2 plus fc1 minus fc2. You will get two frequencies. So these two are the higher frequencies. So low pass filter doesn't allow the output here. Second case, this one is multiplied with second local oscillator. The output becomes minus a square by 2 1 plus cos 2 pi 2 fct. Minus a square by 2 is allowed by the low pass filter 2, and this is not allowed by the low pass filter. So a square minus a square by 2 is less than 0. So the decision device, it compare with threshold level, that is less than 0. It produces output is in the favor of bit 0. This is the operation of coherent FSK. Now I am going to discuss non-coherent FSK. In non-coherent FSK, see here, I am not using any local oscillator carrier at the receiver side. Right? Now here BFSK S of t signal you will get. Right? For example, if see here, if bit 1 is transmitted, my S of t signal equation is A cos 2 pi fc1t. Right? Now in this detector I am using two band pass filters. The band pass filter 1 is tuned to fc1, the band pass filter 2 is tuned to fc2. Right? If this signal, this modulated signal is passing through band pass filter fc1, it is tuned this signal, so it allows this signal. And here this signal is passing through fc2, this signal is not tuned to fc2, so that this signal is not allowed by this band pass filter. Okay. Now this here I am getting a FSK signal, right? This FSK signal is passing through envelope detector. Envelope detector will give the envelope of input signal. Envelope detector, it gives the envelope of input signal. So here getting, it produces a signal which is only amplitude signal. Amplitude. Right? So output of this one is, for example, it allows only first signal, and this signal is not allowed this carrier signal. Why? Because the band pass filter is tuned to fc2. It is not allowed. The envelope detector output is 0. Here amplitude of this one, here it allows the envelope detector. So by adding these two, I am getting a value that is greater than this one, greater than S. The decision device value is greater than 0, whatever the output. For example, it is called as A plus A volts, that is greater than 0. So that the decision device will produce output in the favor of bit 1. Similarly, if bit 0 is transmitted, output signal is minus A cos 2 pi fc2t. So for this case, the band pass filter 1 doesn't allow this signal. Why? Because it is tuned to fc1. So only the band pass filter 2, it allows this signal. So and it allows the output, and this signal here, this FSK, is passed through envelope detector. So it allows the envelope of input signal, that is here we will get a negative voltage. By adding these two, this is 0 minus negative, here you will get negative voltage. So this negative voltage is less than 0, so that the decision device will produce the output in the favor of bit 0. Right? This is the operation of coherent FSK and non-coherent FSK. Right? The advantage of non-coherent FSK and coherent FSK. Coherent FSK advantages is, this is very simple, and it is advantage is simple and disadvantage is costly. Similarly, the non-coherent FSK advantage is low cost. Non-coherent FSK advantage is low cost. The applications of BFSK, right? It is used in telephone line modem. used for FSK transmission, right? Telephone line modem, it is used. Here the two frequencies of this one is 1070 hertz, another one, 1070 kilohertz, another one 1270 kilohertz. Two frequency ranges. This is FC2, this is FC1. So applications of FSK, BFSK is used in telephone line modem. The two carrier frequency ranges, FC1 is a 1270, FC2 is a 1070 kilohertz, right? Okay. Thank you. I hope you will clear the concept of FSK. Once again I am repeating, FSK definition is the frequency of the carrier signal instantaneously varied according to amplitude of input data signal, right? So input data signal. Here we are discussed BFSK. BFSK means n is equal to 1. So the two levels, that is bit 1 either bit 0. At a time for single TB deviation, either we can transmit 1 or transmit 0. The block diagram of FSK, it consisting of two local oscillator carriers FC1 and FC2 as well as 2:1 mux and polar NRZ. The selection line we are using as polar NRZ and input binary sequence, it produces BFSK. For bit 1, output is a cos 2 pi FC1t, bit 0 minus a cos 2 pi FC2t, right? And see here, example, this is our example. S binary sequence, polar NRZ, local oscillator 1, local oscillator 2. For BFSK 1, it is FC1. Here for 0, it produces FC2. Again 1, FC1. For 0, FC2. The carrier signal frequencies. The demodulated signal is demodulated FSK. So because of FC1, it produces bit 1. Because of FC2, it produces bit 0. Again FC1, again FC2. This is the demodulation, right? I hope you will understand the concept and detection of FSK, that is coherent method and non-coherent method. So in coherent method, this method is also called as a synchronization method. So here we are using local oscillator carrier at the receiver side. So in non-coherent, we are not using any local oscillator carrier. Done? This is the operation of FSK. Now today assignment is first question, define FSK, explain modulation and demodulation, both methods, two methods of FSK with waveforms and calculate bandwidth. Okay, today assignment. Thank you.